In this work, we study algorithms for counting graph homomorphisms that work in some sort of mildly exponential time. This work is by A.Bulatov, presenting, and I'm Dadsetan. For a quick reminder, homomorphism from graph G to graph H is, as usual, a mapping between vertices from vertices of G to vertices of H that preserves the edges. The problem of deciding if there exists a homomorphism from G to H is denoted by graph hom, and its counting version is number graph hom. The question there is to find the number of homomorphisms. It's often very convenient and useful to restrict the general graph homomorphism problem, and it's usually done by restricting the classes of graphs that input graphs can belong to. So in general, graph hom of GH, G and H being classes of graphs, is the graph homomorphism problem where the input graphs, the source and the target, have to be taken from classes G and H respectively. For the counting version, the notation and the meaning is exactly the same. Here we are going to work with restricted graph homomorphism problems where there are no restrictions on the source graph G, and the only restrictions are imposed on the target graph H. The complexity of problems restricted this way is very well understood. Say for the decision problem, Pavel Halyarik-Neshatril gave a characterization of problem solvable in polynomial time. So graph hom of H is solvable in polytime if and only if H is a class of bipartite graphs, and it's NP-complete otherwise. For the counting version, Martin Dyer and Catherine Greenhill proved that the corresponding problem is polynomial time if and only if H is a class of graphs whose connected components are complete graphs with all loops present, or complete bipartite graphs, and it's number P complete otherwise. So, as we see, the polynomial time solvable cases of graph homomorphisms are very restricted and not so frequent. The hardness part of the problem can further strengthen. For instance, a few years ago, Marek Tsigan with a bunch of co-authors proved that if we look at the general graph homomorphism problem, then assuming the exponential time hypothesis, there is no better algorithm than just brute force, just looking at all possible mappings from G to H and counting those that happen to be homomorphisms. This, however, doesn't make it impossible for classes of graphs that admit more efficient algorithms, not polynomial time, but more efficient algorithms than the brute force. And this is what we are trying to do in this paper. So we are using the following concept for a class of graphs. We say that a class of graphs is plain exponential if the counting graph homomorphism problem of H can be solved in time, exponential where the base of the exponent is some constant and the exponent itself is linear in the number of vertices of the input graphs. Well, this also may have some polynomial factor, polynomial again in the number of vertices, and since we're not very interested in this polynomial factor, we usually shorten the notation by absorbing this factor into this big O star notation. Several examples of plain exponential classes of graphs exist in the literature. They include the class of all cliques. For this class, there is an algorithm that solves the problem in time. 2 to the power of the number of vertices of graph G, the source graph. The graphs of bounded degree, bounded tree width. In this case, k in the base of the exponent is the bound on the tree width, of course, and also the class of graphs bounded clique width. Again, K here is the bound on the clique width, and well, this is the result we are going to build upon. So next I'm going to introduce several simple algorithms and build up, well, our new class of graphs and an algorithm for this new class of graphs. So let's start with bounded degree. Suppose that we are given that our target graph H has degree which is bounded by some constant t. Okay, then we list the vertices of G. We will always assume that G is connected, because if it's not, the problem is trivially reducible to connected components of G. So we list the vertices of G, say V1 through Vn, in such a way that for any vertex except for the first one, there is a preceding one that is adjacent to that one, to Vi. So let's estimate how many homomorphisms we can have. Suppose this is our list, V1, V2, V3, and so on. Potentially the first vertex in the list can be mapped to graph H in any possible way, in any way. So the number of options for that is just the number of vertices in H. But every next vertex is adjacent to some of the preceding ones, and since the image of the preceding vertex is already fixed, say V1 has to be connected to V2, and therefore V2 has only at most D options to be mapped, because the degree of the image of V1 is at most D. So the number of images of V2 is at most D. Same for V3 and V4 and so on. So the total number of homomorphisms is therefore bounded by the number of vertices in H times constant 2m-1. What does it mean? Well, this number is already plain exponential, and therefore we can simply enumerate all such homomorphisms. Use a brute force with this a little bit, with this minor improvement. The algorithm for cliques is a little bit more interesting. So the old kind of simple algorithm for cliques works as follows. Suppose our target graph is a n-clique. Take some graph G. The algorithm is going to be dynamic programming, so we are filling up a table. The columns of this table will be labeled by all possible sets of vertices of G, so we have exponentially many of them, 2 to the power of V. And the rows are labeled with the sizes of subcliques of Kn. So with numbers from 1 through n. In row K and column, say, W, we will have the number of homomorphisms from the graph induced by W, from the subgraph of G induced by W, to the k-vertex clique. So how do we compute this value? Well, we go over all possible subsets of W. So let's the current subset is W prime. Then we decide that we will map all vertices of W prime to a smaller clique on k plus 1 vertices or on k minus 1 vertices, and the remaining vertices, W minus W prime, will map to the remaining kth vertex of our clique. Okay, so for any such partition, two things may happen. Firstly, well, it may happen that the complement of W prime is not an independent set, and therefore such a homomorphism is impossible. That's just a bad partition. And in this case, well, this partition will contribute 0 to the total number of homomorphisms. Otherwise, if the complement of W prime is an independent set, then clearly any homomorphism from G restricted to W prime to k minus 1 can be extended to a homomorphism. So, well, a quick calculation shows that, well, all this computation can be done in plain exponential time, 3 to the power of V. Well, later, a a more sophisticated algorithm improve this bound to 2 to the power of v. Okay, well, the next generalization of this approach is clique width, the result that was obtained by Magnus Wallström. So we start with introducing the clique width, because again we are going to build upon this measure and this result. So a graph G has a clique width, say at most k, if it can be constructed using 4 operators, well, maybe applying them repeatedly, that use at most k plus 1 colors. So the first operator is create a one vertex graph and color it any color we can. Second, well, take 2 already constructed graphs and take their disjoint union. 3, connect in the graph we have so far, connect all vertices of one color with all vertices of another color. And finally, we'll change the color of all vertices of color, say, I to color J. Well, as a simple example, let's construct a clique using this procedure. So a one clique is very easy to construct. Well, you just take a one vertex graph and color it, say, one vertex, color it red. To create K2, well, we need to create another one vertex graph, color it, say, blue, and then connect all red vertices with all blue vertices. To create clique K3, we first recolor blue vertices to red ones, add another blue vertex, and connect all blue vertices to all red vertices. To connect K4, well, to create K4, we again recolor all the blue vertices, add another blue vertex, and connect. So this process shows that the clique width of a clique is actually 1. Every graph of clique width at most k can be represented as a sequence of operators like that. And this sequence of operators we will call, well, in this case, k plus 1 expression. So every graph of clique width at most k can be created using a k plus 1 expression. So the algorithm for bounded clique width is again dynamic programming one. So suppose we have a graph H, the target graph, and we have a k expression for it. Take the source graph G. Okay, we again create a big table. The columns are still labeled with subsets, with sets of vertices of G, but the rows are labeled slightly differently. If H is any non-trivial graph, the k expression that represents H contains many union operators when we join 2 graphs together. So if we look at the structure of this formula, we may think about it as follows. So we take some graph, take the disjoint union, then apply some operators, unary operators like recoloring, connecting, etc., etc. Then again join it with some other graph, and again recolor and recolor. So the rows of our table will be labeled with such disjoint unions from the k expression we have, followed by all the unary operators before the next disjoint union. So phi here will be a sequence of unary operators like recoloring or connecting. Okay, then the cell in, say, row H prime and column W will contain the number of homomorphisms from the graph, subgraph of G induced by W to H prime. Okay, so now how do we compute this? To compute this, we make 2 decisions about the W. First of all, every vertex of W has to go either to H1 or to H2. So for W, we choose a partition into 2 subsets. The first subset will be mapped to H1, the second subset will be mapped to H2. Also, we will choose a coloring of vertices from W. Since there are only a limited number of colors, k colors, well, the number of colorings is plain exponential, so we can do that. Okay, so when we fix a partition and the coloring, well, we can compute the number of homomorphisms as follows. First of all, we compute the number of homomorphisms from W to H, to H1. That's one of the existing values already computed. Also, the number of homomorphisms from the complement of W prime to H2. We also know this value. We know this value as well. So what can possibly go wrong? What can possibly go wrong is if there is an H from W prime to the rest, such that the image of the corresponding vertices are not connected by an H in H prime. So what we need to show is that the color of vertices in W prime that is connected by an H to a vertex in the complement will have colors that were connected, or to which for which we have a connect operator in that sequence of unary operators phi. Well, this clearly can be done easily as well. So again, we have to make two decisions out of sort of fixed number of possible decisions, or at least plain exponentially many of possible decisions. And then either things go wrong and there are no homomorphisms like that, or things go well and we can compute the number of homomorphisms using already computed quantities. Okay, so our contribution to this graph measure like clique width is a somewhat generalization of that. So what we do, we introduce another operator. We add another operator to the four clique width operators. Well, this will be a unary operator. We call it inflation operator. So it's applied to a single graph, and it works as follows. First of all, it uses several parameters, like the number of colors, as usual. Also the number of copies. We will make several copies of every vertex of our original graph. And also some sets of pairs that actually show which vertices in the resulting graph we have to connect. And that depends on the colors of those vertices and also the number of copy that those vertices have. So let me show it using a simple example. I will show how to construct a cube from a square using the inflation operator. So the number of colors we use here is 2. The number of extra copies is just 1. And okay, the set of pairs is somewhat complicated, but okay, we'll see how it works. We start with a square, colored say this way, and this will be vertices of copy 0 of our graph. Then we make another copy of every vertex. We'll color them in the same way as the originals. Well, this will be copy 1. Now we need to connect things. So if we look at the first 3 pairs in the list, they basically say how we have to connect vertices in copy 1. So it says that we have to connect all colors to all colors. Say color 1 to color 1, color 1 to color 2, and color 2 to color 2. Well, we'll do that, but we also use the following rule. We only connect 2 vertices if their originals are connected in the original graph. So we will connect, say, these 2 vertices and these 2 vertices because the corresponding vertices in copy 0 are connected, and also this and this, but we will not connect diagonal vertices. Now, for vertices in different layers, well, we need to connect only the opposite colors. So color 1 to color 2, color 2 to color 1, but not vertices of the same color. And again, we use the same rule. The originals have to be connected in the original graph. So clearly, well, these are the only vertices we have to connect. And as is easily seen, well, that's just a cube. Okay, so we say that a graph has extended clique width at most k if it can be constructed through a sequence of the clique width operators with at most k plus 1 colors and the inflation operator with parameters at most k plus 1, k plus 1. Okay, examples of graphs of small extended clique width that don't have bounded clique width include, well, first of all, hypercubes. The extended clique width is only 1. Rectangular grids. Extended clique width is 5. Clique subdivisions by a graph of small extended clique width. Then such a construction increases the ECW by only by 4. So clique subdivision means that we start with a clique, say these are vertices of the clique, and replace every edge with the same graph with that family of bounded clique width, of bounded extended clique width. Okay, how do we solve that? How do we solve problems over graphs of bounded extended clique width? Well, we proved two things. First of all, we show that there is a plane exponential time algorithm that, given the graph, outputs either an extended k expression for this graph, if it exists, or returns null if there is none. And secondly, we proved that if we are given two graphs, G and H, and an extended k expression for H, then we can compute again in plane exponential time the number of homomorphisms from G to H. Well, to give an idea on how this algorithm works, well, it's also dynamic programming on the structure of H. Well, as before, we use this k expression. Well, we label columns with subsets. We label the rows again with sub expressions of the one that represents H. If that sub expression ends with a clique width operator, well, we just do as in the clique width algorithm. So for the inflation operator, well, the idea is basically the same as before, only in this case, for every vertex of, say, from W, a subset of vertices of G, well, we have to make a little bit more decisions. We have to decide which copy of the vertex we are going to map it, and what color of vertex we have to choose. Again, there are two options. Sometimes there will be no algorithms with those parameters whatsoever, and sometimes we can find the number of algorithms from the existing values. So there is basically the same. We also show that there are plane exponential classes that don't have a bounded extended clique width. So those classes include some of the well-known classes of graphs, like, for instance, bounded degree graphs. They are plane exponential, but for a different reason. They don't have bounded extended clique width. Also, mesographs don't have bounded extended clique width, and we can prove that, but they are plane exponential. And so are cliques subdivided not necessarily by graphs of bounded extended clique width, but any plane exponential graphs. Well, we also use some construction to produce plane exponential classes of graphs. For instance, if we look at Cartesian products of graphs, Cartesian product of graphs G1, G2 is a graph with vertex set that is just a Cartesian product of vertex sets of the two graphs, and an edge is there if either the first components form an edge in G1 and the second components are equal, or the other way around. Well, if we start with a class of bounded degree and the plane exponential class of graphs, then the class of graphs consisting of Cartesian products of the two is always plane exponential. So what can we do after that? What are possible future directions for work? Well, first of all, note that basically there are two reasons for a class of graph to be plane exponential. One is to have relatively small number of homomorphisms, like graphs of bounded degree. In that case, we can simply enumerate them all, and thus solve the problem. Well, are there other classes beyond bounded degree that admit few homomorphisms? Well, no. Say, if we try to map a star graph to a graph of very high degree, well, we will see that it has a lot of homomorphisms. But there may be some kind of similar classes. For instance, if you take a class of bounded degree and throw in a constant number of high degree vertices, well, that will be more or less, well, it will be plain exponential, although not of bounded degree. The other reason is the structural regularities in graphs. In that case, homomorphisms, like for cliques, bounded clique widths, bounded extended clique widths, to a large extent are determined by a finite number of parameters, and then we can solve the problem in plain exponential time. So this kind of prompts the question, can this notion of extended clique widths be pushed further to some kind of very much extended clique width? Well, probably yes, because if for clique width we use colors, one parameter, one set of parameters, for extended clique widths we used copies and colors, two sets of parameters, well, maybe we can have more. And finally, probably most interesting direction here would be in which way we can combine the two types of classes. Say, well, the theorem on the previous slide, well, basically told us something about that. Well, perhaps anything else can be done. Thank you very much.